Organic chemistry. This is about the chirality, and you already know what is meant by chirality. So let's start the video. First of all, what is chirality? It is derived from the Greek word that stands for hand. So an object is said to be chiral if the object and its mirror image are non-superimposable, just like our right and left hand. When the mirror image of the object is placed over the original object and they do not overlap as shown in the figure below, then the object and its image are said to be non-superimposable. Like this bottle, this is the mirror images of the right and left hand. They are same. They can be superimposed, so they are not chiral. So molecular chirality was discovered by Louis Pasteur when he successfully separated two isomers of sodium ammonium tartarate. He observed that the two isomeric crystals were non-superimposable mirror images of each other. They had the same physical properties but differ in their ability to rotate plane of polarized light. This property was termed as optical activity. In the polarized light, electrical and magnetic fields randomly orient in all planes. When the non-polarized light is made to pass through polarizing filter, oscillations get oriented in only one particular direction and is called plane polarized light. Okay, as stated, chiral molecules are optically active, which implies that when a beam of plane polarized light passes through a chiral molecule, it interacts with the molecule in such a way that the angle of the plane of oscillation rotates. As you can see here, the angle is rotate. Rotation of the plane polarized light by enantiomers. A pair of enantiomer always rotate plane polarized light to an equal but opposite degree. Example, if a pure sample of S rotate plane polarized light by 10 degree clockwise, then a sample of R is the exact same concentration and under the same experiment condition we rotate the plane polarized light by minus 10 degree counterclockwise. So most biological compounds are chiral. Identification of chiral. Basically, the rule of thumb, chiral carbon centers are carbon atoms that are tied to four different substituents that are placed at the corners of the tetrahedron. So chiral carbon are also referred to as stereogenic carbons or asymmetric carbon atoms. Compound 1 has chiral carbon center as it contains four different groups you can see here. So compound 2 is the mirror image of compound 1. So let's go ahead and sequentially rotate compound 1 about the x-axis in the clockwise direction. The various periods of the rotation are shown below. You can see here the various periods of rotation can be shown here. So as you can see, none of the above stretches the same as the mirror image of compound 2. Thus we can convince that compound 1 is chiral. Before we move on, let's try to identify if the carbon atom in the following three compounds is a chiral atom or not. The carbon atom is chiral because it is tied to four different groups. Here, this carbon is not chiral because it is not tied to four different groups. It is tied to HNH2, CH2, CH2, CH2OH, and CH2, CH2, CHOH. The last two groups are identical. This carbon atom is chiral because it is tied to four different groups. Here, this is tied to four different groups because there is a OH on this side. So obviously, this is a chiral one. Enantiomers plus minus and R and S isomer are chiral compound and mirror images are referred to as enantiomers. So we can define enantiomers as being two stereoisomers that contain asymmetric carbon atoms and are related to each other as non-superimposable mirror images. Enantiomers differ only in their optical activity, that is, direction in which they rotate plane polarized light. If an enantiomer rotates light to right or clockwise, it is said to be plus or dextrorotatory. On the other hand, if the plane polarized light is rotated to left in a counterclockwise, the stereoisomer is called as minus or levorotatory. Enantiomers have the same physical properties except for direction in which they rotate plane polarized light. Since the isomer has a different optical activity, they are sometimes also referred to as optical isomers. So on the basis of configuration, we can assign them RS system. The method naming enantiomer was developed by three chemists, Kahn, Ingold, and Prelog. There is no correlation between plus minus and R and S stereo chemical labels. An R isomer can be plus or negative. Optical RN isomers has to be made experimentally with the polarimeter. Here, before we can go into the discussion how to assign configuration orient as to a Caroline enantiomer, let us be clear of how spatial arrangement of the tetrahedral carbon with respect to the plane of molecule is depicted. So solid line group present in the plane of molecule. Wedge, solid wedge group pointing out of the plane towards you, and dotted line hashed wedge group pointed out of the plane away from you. Right. So how they're attached? They're attached on the basis of the atomic number, decreasing atomic number. So bromine maximum atomic number, number 1, priority, then chlorine, then fluorine, and then hydrogen. So the priority will be in this way. Now, how to make the R and S? You can see here 1, 2, 3. So this one, this compound is showing anti-clockwise. So it should be S, counterclockwise or S. You can see here the situation in these two groups, two compounds, 1A and 1B. In this one, 1, 2, 3, it is anti-clockwise, so it is S. But in this way, you can see what is happening. This one is 1, 2, and then 3. So it is clockwise, as hydrogen is on the back side. So clockwise mean R or anti-clockwise mean S. Always we were moving from the atom with the higher atomic number to the atom with least atomic number. How we are supposed to proceed if the lowest priority group is not pointing away from us? So what we will do in such case, you will need to select any one of the two groups that are present in the plane of molecule, rotate the molecule about the axis, and stepwise move the other three groups around until the lowest priority is pointing away from you. So you can see here the lowest priority, like if it is Z, it is pointing away from you. So then we can make their isomers. Priority number is assigned to the atoms that are tied directly to the stereogenic carbon, like this one stereogenic carbon. So what happens if there are two substituents with the same rank? In this case, simply proceed along the two substituent chains until you find a point of difference. Let's again understand. Here the four atoms are tied directly to the carbon center are chlorine and carbon atoms C and C respectively. Clearly based on atomic number, chlorine gets the highest priority, but the other three atoms are tied. So in such a case, we move along each substituent chain and see what atoms are directly attached to three carbon atoms respectively. So you can see here lowest atomic number or highest atomic number. So how we can assign the priorities here? Chlorine the first priority, CH2O second priority, CHCC third priority, and CH3 is on the fourth priority. So from highest to lowest priority, it will be R. So the drug development is this thing is very much important with respect to the drug development, because there are two kinds of drugs. One is the like R type or the S type, and mostly in different types of drugs, different either R or S may be working, the other may not be working. I also gave some examples regarding this one. Now, what's the reason for this? The reason is the active enantiomer can easily bind in this way with the active site. So that's the reason one enantiomer is active while other enantiomer is inactive. Okay, here we have example. This is a thalidomide S or R. Enantiomer ratio is extremely important because while one enantiomer is a benefit to the body, other can be highly toxic. So oral enantiomer is effective, which has soothing effect, relieve anxiety, as enantiomer known to cause teratogenic birth defects. So obviously when giving this medicine, we should be focused that the R enantiomer can be given and not the S enantiomer. Here is another drug, human olfactory sensory organ Carel. So the following pair enantiomers smell very differently to us. So R summer of the carbon smell like spearmint leaves and the S one like caraway seeds. In this one, this is a painkiller ibuprofen. S enantiomer has desired pharmacological activity, while R enantiomer is totally inactive. So in different kind of medicine, different isomers may be active or may be inactive. Here we have different examples. You can see from the higher to lowest property like in this one. This is the anti-clockwise, so this is the S type, this one is R type, and this is clockwise. You can see here first priority, second, third. Same is the case here. This is the first priority, right? Then comes the second priority, and then comes the third priority. Same is the case here, but this is clockwise, this is anti-clockwise. Some more example here is the same thing. First priority 1, 2, 3, and hydrogen is the least priority in the back side. So whenever we are doing this, we have to make sure that the least one will be with the dotted line and away from us. So you can see here the priority list, how the priority list is working, and what's meant by this, like wedge shape in front of the screen, and like a bond proceeding behind the paper, this one, while this one is on the plane of the paper. Another example is showing the same thing. You can see here priority will be given to the atom with higher atomic number to the least atomic number. If the priority atom will be on the back of the carbon, then come the atom on the plane of paper, then atom on the front of the paper. So hydrogen will always have the least priority. You can see here this one. Here is the back on the paper. Even then, is priority because it has highest molecular atomic weight. So starting from here 1, 2, 3. So this is R isomer. While this one here is S isomer on the same thing. This one back. So this one from the back to the front. So front. This is the atom on the plane of the paper, and then comes the front one. So that's why it's coming like this. That's very important to understand. We have another one, least priority to highest priority. You can see here this one clockwise, this one anti-clockwise, RS. Same the thing is here. Maximum priority, this one again. This one is anti-clockwise S. This one is clockwise R. Same thing is explained here. And that's it. That's all for the today video. We will see you in another video next time. Thank you very much, and Allah Hafiz.